Ever felt that sinking feeling when a tech upgrade, something that should be straightforward, just spirals into this confusing mess of unexpected errors?
Oh, yeah.
You're convinced everything went okay according to the plan, but then the system starts acting, well, just not quite right.
Definitely been there.
Today, we're diving headfirst into a real-world head-scratcher, upgrading an ABB IRC5 robot controller and its workhorse, the IRB140 manipulator.
Think of it as like giving the robot a brain transplant. You're moving from an older CPU, a DSQC639 running RobotWare 5.13,
Right.
to a newer DSQC1024 CPU with RobotWare 6.1c. On paper, sounds pretty simple.
Yeah.
A basic swap.
Exactly. And to get the real story, we've got this incredibly insightful first-hand account. It's from a YouTube video detailing a very similar upgrade attempt. It's quite revealing.
Okay.
Plus, we have the robot's actual programming laid bare. We've got the original task and target definitions, alongside a version labeled different values at backup restoration.
Okay. So we can see the before and after, potentially?
Precisely. Our mission here is to really dissect this upgrade experience, zero in on those sneaky reasons things go wrong,
Yeah.
and hopefully equip you, the listener, with the knowledge to maybe sidestep similar robotic nightmares. We want to understand why these glitches happen and, crucially, what you can actively do about them. The countermeasures.
That's good. So let's start with that YouTube account. The initial steps they described were pretty much textbook for this kind of upgrade.
Okay.
They took a backup of the old system, standard procedure. Then, and this is a really key step, they used the ABB system's own tools to migrate that backup.
Migrate. Mimo.
It essentially converts the backup file format so it's compatible with the newer RobotWare version, 6.16 in this case.
Yeah.
It's not just copying, it's translating the data structure.
Gotcha. So it's like translating a document so the new software can read it properly?
Exactly. A good analogy. After that, they generated a completely fresh, clean operating system on the new hardware, running that new 6.16 RobotWare.
Right, starting fresh.
Then came what seemed like the logical next step, restoring that newly migrated backup onto the new system.
New brain, data translated to be compatible. Should be smooth sailing from there, you'd think.
You would think. But cue the suspense, right?
Huh. So what was the first snag they hit?
Well, the first real warning sign popped up during the restoration process itself. The system actually flagged an alert about a software version mismatch.
Wait, even though both the migrated backup and the new system were supposedly running the same 6.16 RobotWare.
Exactly. Both 6.16. That's the first big clue that something isn't quite as straightforward as the label suggests.
That's odd. Like your phone saying an app isn't compatible with the new OS even when the App Store insists it is. Did they proceed anyway, despite the warning?
They did. And, at first glance, everything seemed okay after the restore finished.
Really?
Yeah, the program module, it's a core set of instructions, the robot's routine.
The actual rapid code.
Right, the rapid code. That seemed to be present. And even the configuration for the device net, which handles comms with external stuff like sensors and actuators. That looked normal too.
So on the surface, it looked like a success, like the transplant worked.
It really did. But the real test came when the operational team, the people who actually work with the robot day to day, they reported a critical issue.
Here we go.
The robot just wasn't moving right. Its paths, its final positions, they were off, inaccurate.
Okay, so the users noticed the difference immediately.
Absolutely. And that immediately triggered a much deeper investigation. They needed to figure out what had gone wrong under the hood.
And that's when the real troubleshooting must have kicked into high gear. They probably started comparing things, right? Like the program module from the restored backup versus the original.
They did. They compared the restored module with the original version they'd backed up before the whole upgrade process started.
What did they find?
Okay, and here's where it gets really interesting and maybe a bit confusing at first. Initially, when they compared the pre-migration backups program module with the program module inside the migrated backup folder.
Before restoring it, you mean just comparing the original backup to the translated one?
Exactly. Comparing those two, they found no differences in the actual program logic. The migration tool itself seemed to have done its job correctly. It translated the format without messing up the code.
Hold on, so the translation was perfect, but the robot was still acting up after they loaded that perfectly translated data onto the new system.
Precisely.
So what was the missing piece? Where did the error creep in?
The crucial insight, the realization they came to, was that the problem likely wasn't the migration step itself. It was something that happened during the restoration of that migrated backup onto the new controller hardware. It seems like the act of restoring the data, loading it onto the fresh 6.16 system, subtly altered the program module. Like the new system made some kind of unexpected silent edits during that loading process.
That is incredibly subtle and must have been super frustrating to diagnose. It's like, your perfectly translated document gets secretly rewritten while it's being copied onto a new computer.
Exactly. Very tricky. So the proposed countermeasure, the solution, wasn't about remigrating the backup again. It was about taking a more hands-on approach after the restore seemed complete.
Okay. What did they suggest?
They suggested two main options. Either manually copy the program module file directly from the clean migrated backup folder before doing the full restore operation.
Sort of preemptively replacing it?
Kind of. Or, if they'd already done the full restore and suspected the module was now corrupted, the approach was to actually delete that suspect program module from the controller.
Okay.
And then manually load a fresh, clean copy of it from the migrated backup folder again, replacing the potentially altered one with a known good one.
Okay. So the key takeaway from this whole real-world saga is crystal clear. You just cannot assume the restore process is flawless. It might look like it worked, but you absolutely must compare the program running on the robot with your backup.
Both backups, ideally.
Yeah.
The original pre-migration one and the migrated version.
Right. And you have to be ready to manually intervene to potentially reload modules if you find any discrepancies. This comparison and potential manual fix is a critical countermeasure.
It really is. It highlights the need for vigilance. Now, let's shift gears slightly and look at the second part of our deep dive. The actual robot task and target definitions themselves.
Okay.
This gives us a really detailed, almost microscopic view of the kinds of changes that can happen at the data level. And more importantly, why those specific changes can lead to the sort of problems the YouTube folks encountered.
Right, connecting the bad movement to the specific data corruption. We have those original definitions and the different values at backup restoration versions.
Exactly. So this is like examining the robot's, its configuration DNA before and after the upgrade process to see exactly where mutations might have occurred during that restore.
Good analogy. What kind of data are we looking at here?
We see all the fundamental data types that define how the robot operates. There's tool data, which describes the tool attached to the robot, its dimensions, weight, the precise location of its tip, the tool center point, or TCP.
Crucial for accuracy.
Absolutely. Then there's WOB data, work object data. This defines the coordinate system of the part or fixture the robot is working on. It tells the robot where the workpiece is in relation to its own base.
Also fundamental.
Totally. We also see joint target, which specifies the exact angle for each of the robot's joints axes 1 through 6.
Okay, the robot's posture.
Yep. And ROB target, which is probably the most common one people think of. It defines the robot's target position and orientation in 3D space, using Cartesian coordinates, x, y, z, plus orientation, usually as quaternions.
The point it needs to reach.
Exactly. And then there are various other numerical parameters, things controlling speed, speed data, persistent variables, PRS-num, orientation data, PRS-orient, and so on.
Okay, so let's zoom in. Let's look at some specific examples where the original file and the different values file actually diverge. What kind of changes are we seeing that could make the robot go haywire?
Okay, let's start with a tool definition. Tool sensor. This probably defines a tool used for some kind of sensing operation.
Yeah.
Now, if we look closely, the position vector, the first bit, third element, it's 129.37 in both original and restored.
Okay, no change there.
And the TCP offset within that, the by off 50 part, the Y offset is 50 in both. So this particular tool definition seems stable.
Which is good, but you still have to check, right? Because if the tool definition did change unexpectedly.
Oh, absolutely. If the robot thinks its tooltip is somewhere else or the tool weighs something different, it throws everything off, forces, positions, sensor interpretations. Checking even seemingly stable stuff is vital.
Right. So what about something that did change? Something more dramatic?
Okay, take a look at center board 20 gram. This is WOB data, remember, defining the work object, maybe a specific edge the robot needs to find or work on.
Got it.
Look at the third element of the position vector, the Z coordinate. In the original, it's 567.85. After the backup restoration and the different values file, it's 430.85.
Wow, that's, let me see, over 130 millimeters difference just in the Z height of where the robot thinks that work object is.
Exactly, a massive shift. This really highlights a crucial point. The robot's understanding of its workspace, defined by these work objects, is absolutely fundamental. Any change here ripples through all program points defined relative to that object.
Yeah, 130 millimeter shift. That's not subtle. I could completely throw off any process depending on that location. Welding, gluing, assembly, anything. The robot would be working in the wrong place entirely.
Precisely. And it's not just the position. Look closely at the quaternion values, the second part, which define the orientation of this work object.
Okay, the rotation part.
Right. They've also changed noticeably. See, the first value goes from about 0.707 to 0.695. The second changes similarly. Now, quaternions represent 3D rotation, and even seemingly small changes here can mean the robot approaches a point with a slightly different tilt or angle.
Which could be critical for things like inserting a part or aligning a tool correctly.
Absolutely critical for precision tasks. So this reinforces that idea that the restoration process somehow introduced these subtle but really significant alterations to the robot's basic spatial awareness. It changed how the robot perceives its environment.
And it's not just about how the robot sees the world, is it? You mentioned joint target values earlier. Are we seeing changes there too, affecting the robot's actual physical configuration?
We are. Let's look at J-crouched. This is a specific set of joint angles, likely meant to put the robot into a safe or intermediate crouched position.
Okay.
Now, some of the joint angles, like the first three, show only very small differences, maybe negligible.
Yeah.
But look at the last three joints, axes 4, 5, and 6. Yeah. Joint 4 jumps from 2.7 degrees to nearly 92 degrees. Joint 5 goes from 10 to 32. Joint 6 flips from near 0 to 93.
That's not the same posture at all. That's a completely different configuration for the robot's arm and wrist.
Exactly. You absolutely wouldn't expect the robot's basic stored postures to change like this during a software restore, unless something went seriously wrong. It shows that corruption isn't just about external targets. It can affect the robot's internal state definitions, too.
This could lead to totally unexpected movements, maybe hitting limits, or even getting into a singularity where it loses control.
Potential for all of that. This really hammers home the need for that post-restoration comparison we talked about from the YouTube source. You have to verify these things.
No kidding. Are there other examples?
Yeah, we see similar, though maybe less dramatic, variations in other joint targets like J-Pasos and Sasato. The second and third joint values show bigger changes there, suggesting unintended shifts in how the robot moves between points, maybe during a sensing routine.
Okay, let's look at a ROB target now, like Palisia board. This defines a specific point in space, X, Y, Z, and the tool's orientation there. What changed?
Both parts changed here. The Cartesian coordinates the XYZ position and the orientation quaternion. X shifts from 110.92 down to 81.5. Y goes from 192.7 down to 159.4. Z drops from 3.2 to 1.0.
Again, significant positional shifts. That would directly change the robot's path.
Definitely. And the orientation quaternion values are also clearly different. So the robot wouldn't just be in a different place, it would also be facing a slightly different direction when it got there.
These aren't just tiny rounding errors, are they? These look like fundamental alterations that would directly mess up the robot's intended motion and where it ends up.
Absolutely. And consider pipo sensato. This sounds like a target used for sensing a tube, maybe finding its position. The changes here are even more striking. The original target is near the origin, X and Y close to 0, Z at 16.6. The restored version, X is 81.8, Y is a negative 40.5, and Z is near 0. It's like the robot now thinks this sensing point is in a completely different quadrant of its workspace.
That's not a subtle deviation anymore. That's like it lost the map entirely for that point. It could miss the tube completely or try to sense an error.
Precisely. The potential for process failure there is huge.
Yeah.
We also see changes in PR's num variables. These are just persistent numbers the program uses. For instance, positio, maybe start position counter, changes from 15 to net equal 110. That could break logic loops.
Yeah.
And velpinta, which looks like speed data for painting its first element, maybe the linear speed, jumps from 11 units to 50. That could drastically change the paint application or cycle time.
So even simple numbers aren't safe. Okay, let's tie this back to the bigger picture. What are the real-world consequences we'd expect from these kinds of data discrepancies we're seeing?
Well, the consequences map directly onto the problems the operational team saw in that YouTube video. You'd get incorrect robot trajectories. The path it follows is wrong.
Right.
Which leads to positioning errors, affecting accuracy and repeatability.
Yeah.
This is death for many automated tasks.
Absolutely.
There's a very real risk of collisions hitting fixtures, tooling, the workpiece itself, because the robot isn't where it thinks it is, or the work object isn't where the robot thinks it is.
Costly crashes.
Very costly. Automated processes that rely on that precision would just malfunction. Cycle times could change unexpectedly because of altered speed data, like that velpinta.
Messing up production flow.
Exactly. And any task involving sensors would likely go haywire because the robot's basic understanding of its tool or its environment has been corrupted. Sensor readings wouldn't make sense in the context of the wrong positions.
It really paints a clear picture. Even if the main program code, the rapid logic, seems to load okay after an upgrade or restore, if these underlying data definitions, tools, work objects, target speeds have been silently changed,
Yeah.
the actual physical outcome, what the robot does, can be drastically different and potentially very damaging, very expensive.
Couldn't have said it better myself. This detailed comparison between the original and different values files really underscores why that thorough, meticulous comparison of all relevant configuration files and program logic is absolutely critical after any system migration or backup restoration.
It's not optional.
Not at all. You simply cannot assume everything transferred without error. This comparison needs to be a standard part of the procedure, a fundamental countermeasure to prevent this kind of unexpected, dangerous behavior.
So let's try and summarize what we've unpacked here. It seems abundantly clear that these robot system upgrades, these backup restorations, they're not always the seamless push-button processes we might hope for.
Definitely not always plug and play.
We've seen from that first-hand YouTube account how unexpected changes can just creep in. And crucially, not just during the initial migration of the backup format.
Right, the translation step.
But also during the seemingly straightforward act of restoring that supposedly compatible backup onto the new, clean system.
And what's really insightful is how that YouTube account strongly points the finger at the restoration process itself as the likely culprit, the point where the system appeared to silently alter the program module.
Yeah.
And our deep dive into those program definition files, comparing the original with the different values, powerfully backs this up. We saw concrete evidence of changes, big changes in work objects, target positions, joint angles.
Changes that weren't there in the migrated backup before the restore.
Exactly. Changes that seem to have happened during the restore.
And as we've really hammered home, meticulously comparing these configuration files and program data after any such operation isn't just, a nice to have. It's an absolutely essential countermeasure.
Non-negotiable, really.
Because even those seemingly small differences in a coordinate or a joint angle or a speed value can have massive, costly consequences on how the robot actually behaves, leading to errors, collisions, process failures, the whole 9 yards.
Which means manual intervention might be needed. Corrective actions like selectively reloading specific program modules from that known good migrated backup, or maybe even manually re-entering or verifying critical parameters like tool or work object data might be necessary.
You have to verify. You can't just trust the automated process blindly. Verification and potential manual correction are absolutely key to ensuring the system works reliably after an upgrade or restore.
Precisely.
This whole deep dive really makes you pause and think about the increasing complexity of automation in general. If these kinds of subtle, potentially hidden errors can crop up in a relatively self-contained robot system like this, what are the bigger implications for large, interconnected, automated factories, places where software and hardware integrations are even more complex, with systems talking to each other all the time?
That's a really important question. The potential for cascading errors or unexpected interactions definitely grows.
So what proactive measures can companies implement, maybe system-wide, to catch these kinds of issues early? How do we ensure reliable, safe operation as automation gets even more deeply embedded in everything we do? It's definitely something critical to think about moving forward.
Absolutely. And on a practical level, for anyone listening who works directly with these ABB systems, the IRC5, the RB140, we strongly advise you to really dig into the specific documentation from ABB.
Read the manual, basically.
Well, yeah. Pay close attention to their recommended best practices for backup and restore procedures for your specific robotware version. Understand the tools, understand the potential pitfalls they mentioned.
Forewarned is forearmed.
Exactly. A thorough understanding of these processes, knowing where things can go wrong, can save you a massive amount of time, frustration, and potentially expensive damage down the line. Maybe even consider developing a rigorous post-upgrade, post-restore verification checklist for your facility.
Like a standard operating procedure.
Yeah, that includes these detailed file comparisons we've been talking about. Make it routine. Make it mandatory.